Hello, everyone. I'm Gray Lu, a PhD student from the Institute of Computing Technology, Chinese Academy of Sciences. Today, I will present the paper Lumos towards better video streaming QoE through accurate throughput prediction. HTTP-based video streaming dominates the internet traffic nowadays, standardized as Dash. In Dash, the player runs ABR algorithm to select bitrates for in chunk in order to optimize QoE. The typical form of QoE is like the following equation, including three atoms, corresponding to higher quality, less rebuffering time, and fewer quality switches. I will give a simple example to show how ABR works. The basic ABR algorithm, named read-based, predicts throughput in the future and select bitrate no more than the predicted value, just like this. ABR algorithms can be classified into four categories: read-based, buffer-based, mixed, and learning-based. Note that read-based and mixed originally require throughput prediction. Buffer-based and learning-based tend to rely on throughput prediction when developed in real-world environments. This trend can be seen from Bowler to dynamic and from pensive to ABRL. In this case, accurate throughput prediction is vital to improve QoE of ABR algorithms. Let me give a real case of robust MPC to show how inaccurate throughput prediction decreases QoE. We can see that there is a huge gap between real throughput and predicted throughput. Well, how does that affect QoE? Although the real throughput is high enough for highest quality, robust MPC still keeps selecting lower quality for three chunks, resulting in unnecessary quality reduction and thus QoE decline. This scenario of throughput fluctuation is quite common in the real world. Previous works attribute this only to the change of network conditions. However, it seems that throughput changes in the same trend as chunk size does, like the following picture. This indicates that chunk throughput may be not only determined by network conditions. So our goal in this work is to study a fundamental problem in ABR streaming, that is, how to achieve accurate throughput prediction to assist the ABR algorithms to optimize QoE. We aim to build an accurate predictor. A predictor contains three components: input features, output target, and mapping function. So there are also three key problems. What factors assist to achieve better prediction? Which one of throughput and delivery time is a better target to predict? And which model is more suitable for prediction? Correspondingly, our solution includes three steps. First is identify features. Second is select target and model. Third is implement predictor. Let's start from the first part, identify features. In this part, I will first show you how academic research evolves in this area. Previous works found that background traffic makes it hard to predict chunk throughput. Similar connections exhibit similar throughput patterns. Traffic policy impacts video throughput. And chunk size is useful to predict delivery time. Finally, it's our work. We build a theoretical framework containing all factors impacting throughput and delivery time in video streaming. There are 2 points need to be noticed. The first is delivery time can be calculated from throughput with chunk size given. So factors impacting throughput necessarily impact delivery time. The second is application throughput is determined by both available bandwidth and delivery rate. Available bandwidth depends on network conditions, while delivery rate is heavily affected by application behavior. This is overlooked by previous works. So our work is the first to distinguish application throughput and available bandwidth in video streaming. Now we focus on a unique behavior of video streaming named on-off. It means the player requests for chunks periodically rather than continuously after the startup phase because there is enough buffer. On-off period, you will call slow start restart of the transport layer. If off period exceeds a timeout, the server will reset congestion window to its initial value and return to slow start phase for the next transmission. According to that, we can divide the request pattern of the player into two states, that is buffering state and steady state. In buffering state, CWND is adjusted continuously in subsequent chunks. In steady state, slow start restart occurs when delivering each chunk. As we already have a theoretical framework, the next step is verify it by data analysis. To collect data, we build an automated video streaming measurement platform in the real world. Please refer to our paper for details. We collect the information from both client player and server transport layer, including playback information, signal strength, and TCP information. In all, we collect data of over 2,500 video sessions containing over 300,000 video chunks in a year and a half. By data analysis, we obtain several interesting observations. We first focus on factors in our framework and their influence on throughput. Observation 1. Path throughput and target chunk size are the two most important factors in throughput prediction. It is easy to understand that future throughput is affected by past samples. The question is, how does video chunk size affect application throughput? Observation 2. Correlation between throughput and chunk size is deeply affected by player state, relative chunk index, and signal strength of the client. We can see from the following figure that the correlation in the steady state is higher than that in the buffering state. This is because in the steady state, the congestion window of the server increases independently for each chunk. And before congestion occurs, larger chunk size leads to higher throughput. We can also see that the correlation decreases as relative chunk index increases. And it is similar for bitrate level and network condition. These results all indicate that application throughput is determined by both available bandwidth and delivery rate. For now, we have identified features of the predictor, including 3 parts: player state, chunk information, and network conditions. We use player state and chunk information to represent application behavior of video streaming. Next, let's focus on the second part, select target and model. First is output target. Throughput and delivery time can be converted to each other with chunk set given. Previous work takes them as the same in bitrate selection. Most work use throughput because it is corresponding to bitrate, while recent works start to use delivery time. However, there has been no work studying which one is better for ABR. And the next is mapping function. There are 3 off-the-shelf data-driven methods: multiple linear regression, decision trees, and deep neural networks. We all know DNA is effective. However, recent work shows that it is heavyweight and short of interpretability, and thus how to deploy. Given that we need to deploy the predictor on our real-world platform, we select MLR and decision trees. We conduct control experiments To select target model, we build 4 different predictors as the following table. For metric, we use absolute normalized prediction error following previous works. Note that the predict throughput is converted to delivery time for conversion. And this is the result. Observation 3. Throughput prediction achieves better accuracy than delivery time prediction does. It's very interesting. This indicates that if you want to predict delivery time, you'd better build a throughput predictor and then convert its prediction to delivery time. The question is why? We found the root cause is a long-tail distribution of delivery time. It causes data-driven predictors tend to overestimate the real values. We can see from the following picture that delivery time is more long-tailed than throughput. This phenomenon is known as a character of the wild internet. Because of that, delivery time perceives more prediction error than throughput predictor does. Here is a case to show how delivery time predictors overestimate the real values. Finally, we can focus on the last part, implement the predictor. Let's back to the 3 problems. Now we have their answers, and this is our design principle. For the first question, we use 3 aspects of features as input, including player state, trunk information, and network conditions. For the second question, we use throughput as output target. For the last question, we use decision trees as the mapping function. Based on those, we propose Lumos, decision tree-based throughput predictor for ABR streaming. We build Lumos by regression trees and use CART to train it. For dataset, we selected over 700 ABR video sessions in real world collected on our platform. We balance the data for training decision trees. And then we deploy Lumos in dash.js player by dumping its parameters in JavaScript. Since Lumos is a predictor, it can be integrated into any ABR algorithms with prediction. We use 3 algorithms as examples. For RB and MPC, we replace their harmonic mean predictor with Lumos. For BBA, since it doesn't rely on prediction, we modified its linear function and combined the prediction of Lumos with it in order to show the advantage of accurate prediction. We evaluate the algorithms in the real-world internet on our video streaming measurement platform. We conduct tests on over 300 sessions under various network environments. As for metric, we use both prediction error and MSE to evaluate prediction accuracy, and use QoE I mentioned before to evaluate performance of ABR algorithms. Let's first focus on prediction accuracy of Lumos. Overall, Lumos significantly reduces prediction error and MSE compared to other methods. It is notable that under strong signal strength of Wi-Fi, the prediction error of Lumos is remarkably low, with only 7.4% in average. Here is an example. We can see that prediction of Lumos is quite accurate under this condition. Even under weak signal strength, where network is hard to predict, Lumos still improves prediction accuracy over the 2 metrics. Since harmonic mean is widely used in ABR, we compare Lumos with it and summarize why Lumos is better than HM. The first reason is Lumos is aware of network conditions and player state. It makes Lumos perform better in the startup phase. The second is Lumos takes the fluctuation of chunk sizes into consideration. It makes Lumos perform better under strong signal strength. And under weak signal strength, Lumos reacts quickly to bandwidth fluctuation. In a word, Lumos can distinguish the change of network conditions and application behavior. The last part is QoE of Lumos-assisted ABR algorithms. With MPC, with RB and BBA, we can conclude that Lumos-assisted ABR algorithms performs better than their original versions. These results show the benefit of accurate prediction of Lumos. And we also compare MPC plus Lumos with Pensive, a state-of-the-art reinforcement learning-based ABR algorithm. We can see that MPC plus Lumos performs much better than Pensive in the real world. This is partly related to the difference between Pensive's simulator and the real world. For summary, we list our contributions in this work. First, we construct a theoretical framework containing all the impacting factors in predicting throughput and delivery time for video streaming, and distinguish application throughput from available bandwidth for the first time. Second, we build a real-world video streaming measurement platform and collect extensive datasets. By data analysis and controlled experiments, we found that strong correlation exists between chunk size and throughput. This correlation is deeply affected by player's state, relative chunk index, and signal strength of the client. And throughput is a better prediction target than delivery time in terms of prediction error for data-driven predictors. Based on those, we propose Lumos, a decision tree-based accurate throughput predictor for ABR streaming. As a plug-in, Lumos assists ABR algorithms to achieve better QoE. My presentation is over. Thank you.